So remember in our last lesson, we talked about parent graphs. And then in today's lesson, we're going to talk about the transformations that we can then do to those parent graphs. But remember, we talked a little bit about what's called our greatest integer function. But remember that we wanted to kind of explore a little bit more what that means for us. Because we also need to know how to plug things in and evaluate our greatest integer function. So remember, we looked a little bit about what this looked like. So it is also called a step function. Okay, and so the definition of a step function is going to be a function that increases at specific integer intervals resulting in a stairway graph. And we can kind of see it over here on the left-hand side. Notice that each one of our lines is going to be one of our steps. The biggest thing to notice is that on the right side of each of our steps is an open circle. And the reason for that is because if they were closed circles, notice that it would not pass our vertical line test. So remember the notation for the greatest interval function, which is a specific type of step function, is going to be the double backed hard bracket. So notice that we can plug in any number for our x. But for our y, notice that we're only going to get out whole numbers, which means that this is going to be all integers. And the way that we read this, or the way that we think about it, is going to be the greatest integer that is less than or equal to x. And that's going to be important when we start trying to actually plug things into a greatest integer function. So it says evaluate the function when x is -1, 2, and 3/2. So we have a greatest integer function, and then we're going to be adding 1. So if I wanted to plug in -1, I'm plugging the -1 in for my x, just like I normally would. And so I would be saying, what is the greatest integer that is going to be less than or equal to -1? And because -1 is already an integer, and it can be less than or equal to whatever we have inside there, it's just going to be -1. And that's going to be true for any of our whole numbers that we plug in. So the same would apply if we wanted to plug in a 2. So we would just end up with 2, and overall we would get 3. What changes is when we plug in a fraction. So notice that 3/2 is not a whole number, it's not an integer. Therefore, we have to get out an integer when we plug it in. So remember that 3/2 is equivalent to 1.5. So we're saying what is the biggest integer that has to be less than or equal to 1.5. And so that would be 1. And so we would evaluate it, and we get 2. Now, it doesn't ask us to find this, but I want us to think about this if it was a negative. So if I had negative 3/2, notice that would be negative 1.5. So we still have to have the biggest integer that is less than or equal to negative 3/2. Be careful, because a lot of people's first instinct is to say -1. But think about -1 is not going to be less than or smaller than negative 1.5. So this would actually be -2, because -2 is going to be the closest integer that's going to be less than or equal to negative 1.5. And that's kind of a little bit about our greatest integer function. All right, so going on, remember that we have different types of transformations. The first type are the shifts to our graphs. So we can have excuse me, vertical and horizontal shifts. So we can either move it up and down, and then also left and right. So remember that if we're adding or subtracting a number to the outside of the function, that's going to move it up or down, and it's just going to be the same direction of the sign. If the addition or subtraction is on the inside of the function, it's actually going to do the opposite of what our operation is. So if I have minus c, it's going to move it to the right. If I have plus c, it'll move it to the left. And we'll look at what I mean by inside and outside of the function here in our next slide. So we want to start with the graph f of x equals x cubed. And remember that this is going to be our cubic function, and it is going to be our parent function. So we have f of x equals x cubed. And I'm going to plug in a couple of points just so we can get a basic idea of what that graph is going to look like. So if I plug in -1, notice we would take -1, plug it in for x, cube it, and we would also get out a -1. We plug in 0, we would get out 0, and if we plug in 1, we would get out 1. So these are going to be our 3 points. But then also remember, if we were to continue on, if we plugged in 2 cubed would be 8, and then -2 cubed would be -8. So our graph kind of looks like 2 halves of a parabola. They just happen to be facing kind of opposite directions. And so that would be our parent function, and that's the graph we want to start with. But notice that that's not what they ask us to actually graph. So in part A and B, they ask us to do a couple of things. On the first one, they ask us to find g of x, which is x cubed minus 1. So I'm going to start with the green graph, or our parent graph that I had. And basically what I'm going to do, because this -1 is outside of my third exponent, that means that I'm going to move it up or down. Because it's subtraction, that means I'm going to move it down. So I'm going to take all of the points on my graph and move them down. It's still going to have the same shape as our parent function. Basically, it's like I've copied and pasted everything just down one unit or one block on our graph. So then on our next graph, we're finding h of x, and they tell us that h of x is going to be x plus 2 quantity cubed plus 1. So notice that this time the plus 2 is on the inside of our cubed, or the third power, and the plus 1 is on the outside. So the plus 2 on the inside is either going to move it left or right. But remember that because it's on the inside, it's actually going to be the opposite of what our sign is. So instead of moving right 2, because it's positive, we want to do the opposite of that and move left 2. And then we have a plus 1 on the outside, so that's going to move everything up 1. Now remember that when I say left 2, up 1, I'm talking about from my parent graph or my starting graph. I always want to start with that parent graph, or basically the simplest graph that we have. So I'm going to move all of my points left 2, up 1. And again, remember, it's just like I've copied and pasted that graph, so it's still going to have the same shape. And so that would be our final graph. And I specifically am using the cubic function here, but this would apply for any of our graphs. If we had a quadratic graph, basically we can take that quadratic and either move it left or right, up and down. If we have an absolute value graph, again, we can move it left and right or up and down. The process is going to be the same no matter what our graph looks like. We could even do it with a graph that we haven't seen before. If we know that I'm supposed to be moving it left or right or up and down, we can still move all of the points of my graph that many spaces. So notice that, or remember that, the next type of transformation that we have is a reflection. And we have two different types. We can either reflect it across our x-axis or we can reflect it across our y-axis. And again, it's going to depend upon if the operation is on the inside or the outside of our function. And what's going to do that is if it's a negative. So if I'm multiplying by a negative to the outside of our function, it's going to reflect it across our x-axis, or it's going to reflect it vertically. If the negative is on the inside of our function, it's going to reflect it across our y-axis, or basically horizontally. So let's look at what that would look like for a graph. This is the graph of the function given by f of x equals x to the fourth is shown in the figure 1.18. So this is our starting or our parent function. Basically, it's still a parabola. It's just a wider parabola. And then since each of the graphs in the next figures is a transformation of the graph, find an equation for each of these graphs. So notice that both of these are pointing down, which is going to be a reflection across our x-axis. But notice also that we have other transformations that have happened as well. And so we're going to have to take that into account. So we're going to have our g of x equals, and we want to start with our x to the fourth. And because we know that the x to the fourth is kind of revolves around the vertex, similar to how our parabola does, we can see that our vertex has moved up 2 spots, and it hasn't moved left or right any. So we're not going to have anything on the inside of our fourth, but we're going to have a plus 2 on the outside of our fourth. And then because it's now facing down, we know that there's also going to be a negative multiplied to the front of our x to the fourth. Right, likewise, we want to look at our h of x. Again, we're looking at this vertex. This time it hasn't moved up or down, so we're not going to have anything being added or subtracted on the outside, but it has moved right 1, 2, 3 spots. So we know that we need to do the opposite operation. So it's going to be an x minus 3, but it needs to be the inside of that fourth power. So I'm going to put parentheses around it. And again, it's been reflected across our x-axis. So it's just going to get a negative on the outside. Now, some of you are thinking, Well, what happens if I plug that negative onto the inside? Well, if we think about it, remember that f of x equals negative x to the fourth. Because this is an even power, we would actually end just up with x to the fourth. And the reason for that is because notice my parabola graph is going to be symmetric about our y-axis, or basically it's a reflection already across our y-axis. So even if I were to flip these two sides, I would end up with the same thing. And that's because if I take a negative to the fourth power, I just end up with a positive as well. Then it's not always going to be the case. Sometimes we'll have things that look a little bit different, like our square root graph is going to look different. And that's because it is not going to be symmetric. And so let's describe what's happening here in words first, and then we'll look at what those graphs mean. We need to make sure that we're using the correct vocabulary. If I ask you to describe the transformations, we need to be able to write that out using correct mathematical vocabulary. So on our first one, again, remember we're talking about from our parent function. My parent function in this case is our radical graph, so the square root of x. So notice that we've added a negative to the outside on part A. So we would want to say that this is a reflection across the x-axis. So remember, if it's on the outside, it's going to reflect it across our x-axis. Now on part B, notice that our negative this time is on the inside. And that's going to be important because, like I said, our square root graph is not symmetric. So this will have a reflection across the y-axis this time. And then lastly, on part C, notice that we have translated or shifted, you could use either word, two units to the left because it's the opposite direction of our sign, and reflected across the x-axis. So again, if I ask you to describe transformations, I'm asking you to use these vocabulary words. I don't want us to just say up one or right two. I want us to use the correct mathematical terms. Likewise, I could also give you a description using these types of words and ask you to find the equation. We need to, remember, be able to go back and forth between our different types of representation. So between an algebraic representation to a verbal representation, and then vice versa, from a verbal representation back to that algebraic. So let's look at what these graphs would look like. So this lighter graph for all of my pictures is going to be the parent function, or the square root of x. So notice on our first one, which was g of x that has the negative on the outside, it's just been reflected. So now it's going to point down instead of pointing up. On our next one, where the negative is on the inside, it's a reflection across my y-axis this time. So basically, instead of pointing to the right, we're going to point to the left. Now, if we wanted it to point to the left and also point down, we could have f of x equals negative square root of negative x. And so that would be a reflection across our x-axis and a reflection across our y-axis. So it would point down into the left. And then lastly on this one, remember that we said it shifted left twice. But because we still have that negative, it's going to be pointing down, but just from that new starting spot since we shifted it to the left. All right, so our last type of transformation are called our non-rigid transformations. And so these are going to be our what we also call our dilations. Or we can also see them called stretches or compressions. I just want us to see all of the different types of words because sometimes one textbook will use one type of word, but you'll see a different type of word on instructions or on a test or something like that. So I just want to make sure we understand what all of those possibilities are. So notice that here, my starting graph or my parent graph is going to be the absolute value of x. And so on the outside, I have two different examples. I have one where I've multiplied by a 3, and I have one where I've multiplied by a 1/3. So basically, we're going to dilate our graph by 3 and by a factor of 1/3. And so let's look at what that does to my graph. So basically, hopefully we remember that this is going to stretch or compress our starting graph. And we are multiplying it to the outside of our absolute value. And if it's on the outside, hopefully we remember, just like with all of our other things, if it's on the outside, it's going to affect us vertically, which is basically towards or away from our x-axis. So we can kind of think about this like slope. So if I have a 3 on the outside, notice that our graph has been stretched away from our x-axis. And so it's going to have a steeper slope, basically. If I put that 1/3 on there instead, now we have been compressed towards our x-axis instead, or it has a not as steep of a slope. Now let's look at our other type of dilation. It's still called a stretch and compress, but because this one would be a vertical stretch or compress, hopefully we can think that, the other option would be a horizontal stretch or compress. So if I have 3x, notice that is actually the same thing. Now, the reason is going to be because if I have the absolute value of 3, notice that the absolute value of 3 is 3. So that's why we get the same graph. Now, that wouldn't always be the case. So notice that if I have a negative on the outside of my graph, it's going to be a reflection across my x-axis. But if we have a negative on the inside of our graph, notice that it's not going to change our original parent function. And the reason for that is going to be because our absolute value graph is symmetric about our y-axis. And so even if I flip it, it's still going to be the same graph. Or we could think about it, the absolute value of a negative is going to give us a positive. So we would end up with the same thing that we started with. All right, now let's look at maybe something that would matter if it's on the inside. So we have a 1/2. Let's see, I don't quite want it to be written that way. So we want to plug in a 1/2 into the inside of our function. So we're going to have y equals, or parentheses, we said that I'm going to plug in a 1/2. I still have an x. And it can still be to the 3rd power. And then we want to add 2. So notice, it's a little bit hard to see. Oh, this needs to have a negative in front. That's why it looks different. Negative. All right. So notice now that when we're looking at our graph, it has made it look different or dilated it, but this time notice that it's actually gone horizontally. And that's because we plugged that number into the inside now instead. So basically, our starting graph was that one. And when we plugged in a negative, so when we plugged in the 1/2 to the inside, it's going to affect it horizontally this time instead. So if we wanted that to be a 2 instead, again, we want it to be negative. Notice that that also affected it horizontally, but it basically stretched it. And the reason that these are called non-rigid is because they're a little bit different for each of our different types of function. They're still going to make it either like narrower or wider, but it's going to look a little bit different for depending on the type of function that we have. And remember that these are also called our A values when they're on the outside. And that's going to be really important in our next lesson when we start talking about piecewise function. Is trying to figure out exactly what do these numbers being multiplied do to our graph.